Director of the Technology Development Applications Group at APTIM. He holds a Ph.D. from Cornell, go New York, and has more than 25 years of experience in contaminant remediation and forensics. Paul?
Yes, sir. There. Thank you very much. I'd like to thank Gene for organizing the Mr. Olympia competition along with the remediation conference. It's made that long walk down the hallway way more interesting than it normally is. Maybe better than Disney World. I'm going to talk about colloidal carbon today for treatment of PFAS, but I'm going to start by going back a little bit for those of us who've been doing this a long time. When we get a new contaminant, sort of what generally happens in remediation? You know, we can start, with me, it go back to like MTBE and PCBs, and usually the chemists cause this problem because they develop a new analytical technique that gets you lower levels, so all of a sudden you can see these things at lower concentrations. Widespread sampling occurs. We have a bit of panic because we start finding these contaminants all over. And then there's tons of research that occurs at universities and you know, federal agencies where we look at fate and transport and degradation. Usually then the next situ treatment approach comes along, followed by some in situ destructive treatment. And we've seen that for all sorts of compounds. And then finally, you know, the end game is sort of natural attenuation. So where are we in terms of the path for PFAS? Well, we've got new analytical techniques thanks to this gentleman. I'm surprised you don't need a bodyguard for developing 1633, because none of the chemists like it very much in the labs. There's certainly been widespread sampling. There's all sorts of panic going on, as we know. I know, you know, the CERTUP and ESTCP organizations have funded more than 170 projects looking at fate and transport and degradation of these contaminants. We have ex situ treatment. We have ion exchange systems and GAC systems that work very well at removing these compounds from water. This is where we're falling short, in situ destructive treatment. We don't have anything at this point that will destroy these compounds in situ to sort of meet what we think the regulatory requirements are going to be. Okay, so what's different about PFAS? Well, again, we're concerned at exceedingly low concentrations, nanograms per liter. If we were concerned about TCE at nanograms per liter, we'd be having the same talk about how widespread TCE is everywhere in the world, because, you know, we're looking at these things. Those of us who draw plume maps, you know, the lower the concentration, the larger the plume. I mean, that's typically what one sees. We have a complex array of structures, as we've just found out. It's perhaps the most recalcitrant class of compounds that we've ever dealt with. So in situ bio, our traditional chemox, our traditional reductive approaches really don't work particularly well for these compounds. So what kind of alternatives do we have at this point for treatment? Well, one would be foam fractionation. That's where, because these things like an air-water interface, you can foam them out of water and then capture the foam. You'll get a lot of PFAS in an air-water interface. Secondly is thermal. We're going to hear about thermal a little bit later, particularly for unsaturated surfaces. But we're also looking now at in situ adsorption or sequestration, so actually trying to bind these things up in the subsurface. Why would we do this? Well, if we don't have a destructive approach, this perhaps is a way to protect down-gradient receptors, drinking water wells, public supply wells, or to reduce the mass flux from source areas so we can get a lot less PFAS coming from those AFFF source areas. What kind of amendments are people looking at? I've got activated carbon in green because that's what I'm going to talk about today. But there's a lot of research going on also with things like powdered ion exchange resin, organoclays, some polymers like polydextrins and polydadmac, and there will be others as we sort of move forward. So let's talk a little about activated carbon. So in situ amendments, activated carbon amendments have been around for quite a while. Often these things are larger particles, you know, GAC and PAC. They're mixed usually with a reactive reagent, something like you know, peroxide or ZVI or bacteria and nutrients. They're injected often under pressure to create fracking into tight formations. So your contaminants sort of desorb to the carbon, and then you've got some type of approach to degrade them at the same time. Now, more recently, we've got much smaller carbon particles, colloidal carbon. So it's 1 to 2 micron. This material almost looks like paint when you sort of work with it. And this has been added to aquifers. It was primarily developed to help treat chlorinated solvents and solvents at low concentrations. So sort of the concept is that this can be injected and it goes into permeable formations. You don't have to inject it under pressure. I've got a little fancy graphic here. So you have your TCE and such. You add your carbon. That enhances absorption and increases concentration at the surface of the carbon. And then you have bacteria. You have some type of abiotic treatment approach that then breaks that down. So you have a combination of sorption and treatment. And you stop your down gradient migration. Now for PFAS, the same type of approach has been marketed. Regenesis has Plume Stop, Cascade has Colloidal Chem, and there will be other products that are like this certainly in the future. But basically the approach now is you can inject this into the ground, again into sort of permeable formations. So we inject our carbon, and you can kind of see, this is a nice micrograph courtesy of Regenesis. You can sort of see sediment particles in situ or sand particles, and then after this carbon absorbs to them, you can kind of see that on the surface. So you're really increasing your fraction of organic carbon in an aquifer is what you're doing. So then your contaminants, in this case your different PFAS absorb, and you prevent down gradient migration. So nice approach, but there's a lot of questions. And those questions are, well, how well can you distribute this material in aquifers? Is it readily distributable, or is it difficult to sort of get into the ground? Secondly, how well does it absorb these different classes of PFAS? And then the question that always comes up is, yeah, but it's just absorption, so at what point are they going to desorb? How long will this last before these contaminants start to desorb? And then fourthly, are there other problems associated with this that you don't think of? Carbon in monitoring wells, you're going to reduce hydraulic conductivity, so those are some of the types of questions that sort of go along with this approach. So our research group has been funded, in this case by the Navy, by the NESD program, basically to take an objective look at this technology and to try and answer all of these different questions that sort of I just discussed. So basically, we have a project, and we're a couple years into this project now. This is occurring at a Navy site. It's a typical AFFF source area site with PFAS in groundwater. And we went through kind of your traditional project tasks of site assessment, some laboratory work, designing and injecting a barrier, and then we're in our starting our second year of groundwater sampling. So I'll show you some of those data to date. And you can see the basic concept. We have a source area. In this case, there's fairly high concentrations, as I'll show you. So the concept is really to reduce concentrations down gradient of the source area and to reduce mass flux of PFAS coming down gradient. So here's a little bit about I'm not going to tell you what the site is, but it's an East Coast Navy site. So essentially, we started out by taking some soil cores, looking at lithology, and then doing some depth-dependent discrete groundwater sampling. We kind of see your traditional AA prime overhead. This is about over 800 feet. And we took samples every several feet, and essentially, as a geologist, always say, well, it's a nice fine sand. You've got a clay above, and we've got a nice clay layer on the bottom. And for those of you who like fine sand, there's a nice photo of some fine sand. And when we did the site assessment work, again, sort of moving down gradient at these different soil bore areas, I'll focus. So we've got PFOS, PFO, and then total PFAS. And the blue line is sort of the total PFAS, and this is by EPA method 537. So again, you're certainly missing some component, but sort of the interesting thing is here, as we move down gradient, you see we have a really high concentration in the shallow zone up toward the source area, and then as we move down gradient, it almost looks like the PFAS is sinking a bit, which we hear a lot about these areas, and that about the air-water interface, and that the PFAS is typically moves a little differently than solvent, stays along the air-water interface. But here's sort of an example where, as you move down gradient, we've got PFAS getting deeper and deeper, and almost certainly there's quite a bit of PFAS also held up in that clay layer. So, as you're doing your site assessment, just be objective, be open, and sort of interpret the data as they come, because these sites can be very complex in how PFAS behaves. So we have a large research laboratory up in New Jersey, the state which started this industry, and you all have jobs because of us, so you're welcome. But basically, we set up a column test, and basically, this was just really a proof of concept. Is this carbon, going to work in this type of environment? So we set up a couple of columns with homogenized sediment, and then to one of those, we added PFAS, or PFAS, yeah. We added colloidal carbon. We added PFAS to both of them, but we added colloidal carbon, and then we passed groundwater through these in an upflow direction. So essentially what we're looking at is, will the carbon absorb the PFAS? And what we did here is we simulated about 2 years of groundwater flow in about 3 months. So we really, pushed the rate of groundwater flow at the site because we didn't want to run a 2-year column test, basically. And we added about 4% colloidal carbon to these columns. And you can kind of see as you look at the columns, you can see the dark one. Doesn't take a genius to figure out that's the colloidal carbon column. So what did we see? So this is the control column. And basically, these are the influent concentrations. This is PFAS, which is there at the highest concentration. This is a fluorotelmer, 82FTS, which is also very high, and you typically do see these at AFFF sites. And these are a range of other PFAS. But the one thing that's noticeable in the control column, well, a lot of these break through very quickly, so we're not getting enhanced sorption. The couple that don't are those that are very concentrated. So the PFAS, you can see early on, so for the first several weeks that we're sort of running these columns, we're not at equilibrium, so there's enhanced sorptive capacity for both of those. And then they kind of reach a point where they're at, or in this case, a little bit above what's going in the groundwater. So not atypical, but this was sort of interesting in terms of the extra capacity. Now for the test column, this is where we injected the colloidal carbon. And basically what we see is once we add the carbon, we're flowing, again, water with these different PFAS through groundwater from the site. And essentially we had near non-detect for all of them. So essentially what this said to us is, okay, this is worth going to the field with and testing for PFAS. The simple proof of concept in the lab suggests that this could work. The other thing we wanted to do, and it's hard to easily quantify colloidal carbon once you've put it in the ground. So we did some testing and basically developed a really simple thermal method to do this, where we just do a high temperature combustion. So we threw these columns in the -80. We cut them with a saw, basically. So, and then we measured small amounts and combusted at 550 in the lab. And basically, what you're looking at is the difference between the carbon column and the control column. And essentially, everything that's sort of not in the control is our carbon that's in the column. And we ended up with about 0.5%, which is not atypical for what you could achieve in the field. Okay, so the next step is to design a barrier. So in this case, we worked with Regenesis and essentially supplied them with all of the site data. This is something that is available. They have a model that they then use and help you design a barrier based upon groundwater flow rate, porosity. You don't have to look at all these numbers, but this is basically what goes into the model. And kind of what comes out is, how wide a barrier do we need, presumably to absorb all of these materials, and kind of how much of your carbon product needs to be added into that barrier. So then if we take a look at the site, basically, we were looking at a barrier that it's a test. This is just a test. And the wider the barrier, the longer it's going to last. But typically, the design parameters for these are something on the order of 15 to 30 years. So, you can try to design these over a reasonably long time frame. Of course, this is an AFFF source area. These are high concentrations. And it would be a little different if you're doing this at maybe the toe end of a plume, where you're really trying to, look at, you have nanograms per liter, but above your regulatory levels. So that's another way that you can look at this. And those, this type of approach there would last an awful lot longer than you would in a source area. But essentially, we put in some wells. We looked at both the shallow and the deep zone, and then basically went in and put a barrier in that's on the order of 12 injection points, which you sort of see here. It's on the order of 10 feet wide, and we're targeting about 2 grams of carbon per kilogram of soil. Now these wells, this S&D, they're again shallow and deep, up gradient, sort of halfway through the barrier, the down gradient edge, and then 5 and 10 feet down gradient. Groundwater flow, of course, is in this direction. Here's what this looks like. So the colloidal carbon product comes in totes. It basically gets mixed with potable water, and geoprobe points are put in, and then it gets injected into the ground. You start deep, you inject the amounts you want, and then basically you pull back up slowly so that you get the entire formation. Okay, so this is kind of what we've measured over time. We've basically done our typical low flow quarterly monitoring. We've done some soil cores. I'll show you some core data just to see how well the carbon distributed. You can also analyze for PFAS adsorbed onto the soil that way. And we're doing some work with passive flux meters, and I'll explain those a little bit as I get toward the end of this. Okay, so let's start with the carbon distribution. So let me just back up a second. If I can figure that out, should be able to. Don't go too far. But essentially here, so we took a core up gradient, which is our baseline, and we took 2 cores within the barrier. So all the way down, pulled them out, sectioned them, and then basically ran this test. We wanted to see how well the carbon distributed. And here's sort of an example of a section where you see a lot of the carbon, and then sort of here's some where you've got high densities and then sort of lower densities. And if we do a subtraction, so the yellow bars are baseline, and of course, as I mentioned, we have kind of this fine sand, some clay toward the top and clay toward the bottom, and you see you do have higher fractions of combustible materials in those fines, which is not unexpected. But if we sort of subtract out, this is kind of where we ended up in terms of the injection. You see some areas where there's quite a bit more, and you see some where you're a little bit under. This was the goal. This was kind of the target goal for carbon distribution. So I would say, this is pretty good. We all know fine sand is not just fine sand. There's always some layering in there. So we probably had sort of some more conductive areas here. But you ended up, believe it or not, if you do the statistics on this, at about 3 grams per kilogram on average, with a deviation of about 3. So there is some deviation there, but this didn't seem like too bad distribution considering what you're trying to do. Okay, so now I'm going to show you the data. And let me just again point out, so you can understand this, where these wells are. So what I'm going to show you are the well sets that are right in the middle of the barrier, at the down gradient edge, and then 5 and 10 feet down gradient. And that sort of runs along this way. So this 1S, this is the shallow zone, and basically the orange bars are pre-injection. So this is what our baseline looked like. And then afterwards, these different colors run out to, this is day 349, which is that pretty sort of magenta color. So we're after a year, about a year after injection. And what we kind of see is that as we move within the barrier, we've still got some PFAS that's in solution. As we get to the down gradient edge, and again, these are sort of short chains down here, 4 carbon up to 8 or 9 carbon. So these are sort of your long chain PFAS. The results look pretty good. With the exception of perfluorobutanoic acid, or PFBA, which is sort of a short chain carboxylic acid. It doesn't adsorb well to anything. So if you do isotherm work and you look at this, even in GAC systems, it breaks through pretty readily. Ion exchange systems, it's one of the early ones to break through. So EPA at this point is not regulating this compound. Let's all have a group prayer that EPA does not decide to regulate this compound, because it's a tough one to deal with. But basically, if you look at the downgrading edge, and this is a log order, so this is basically each one of these bars is a log reduction. So that looks pretty good. You're basically, if you exclude the PFBA, you're at 99.98% removal. Basically, total removal of the larger chain, the longer chain PFAS. So that all looks pretty good. And then at 5 feet down gradient, after a year, you're at about 94% decline. So of course, you've got some stuff desorbing down gradient of the barrier, so you're not expecting great removal right away. But hopefully that shadow will continue as you sort of move along. These are the deep wells, and the story is relatively similar. The only difference is perfluoropentanoic acid, which is the 5 carbon, also showed a little more breakthrough in the deeper zone. It's present, interestingly, at lower concentrations in the deeper zone. But again, at the down gradient barrier edge, all of the long chains are basically removed. So that's a good story. So again, reasonably good performance after 1 year. So now passive flux meters, the other thing we want to look at is, are there any changes in hydraulic conductivity in the aquifer when you're injecting carbon? And secondly, what is the reduction in mass flux? So, mass flux, we always look at concentrations, but mass flux is kind of how much of a contaminant is moving through an area over time, which is a lot of times more important than concentration. If you have a high concentration and no groundwater flow, nothing's going anywhere. So it's sometimes more important to look at how much is sort of moving along through an area, and that's your mass flux calculation. So these are mass flux meters. They're produced right here in lovely Florida by a company called EnviroFlux, which is a spin-off from Mike Annable at University of Florida, who was one of the people who developed this technology. And what you have here is basically you have sort of two different zones. You can see a couple of my guys dropping this sort of passive flux meter into a well. You've got carbon layers, and there's an alcohol that's adsorbed onto that carbon, which desorbs off, and that's how you determine your groundwater velocity. And then you have resin layers that absorb PFAS. So these kind of occur. You drop these in a well at the depths that you're interested in, for presumably the screen depths, for about 30 days, and then you pull them back out. And here's again Greg Lavornia, one of my guys, pulling them out. And basically you cut these open, you take samples, you send them to the laboratory and EnviroFlux, and they run analysis for PFAS. They farm that out probably to SGS, and then they do an analysis of alcohol that's left on the resin. And what you get is you basically get, for each individual compound, in this case, so we have PFOS, PFOA, and perfluorobutanoic acid. What we have here is sort of the Darcy velocity, so the groundwater flow rate, okay, which is good to know, and we're going to see over time whether this changes. So if the flow rate starts slowing dramatically through the barrier, then we'll know, okay, there's some change in conductivity going on here. We can also look at, of course, levels of groundwater. We can do pump testing or whatever, but we're looking at the passive flux meters. And then this, this value with depth is actually your flux. So this is micrograms per square meter per day of flow, of this case in PFOS, and you can see the area where it's maybe higher, up here at around 10 feet below surface, and then down toward the bottom where it's a bit lower. And we'll also sort of take a look at that over time, so reduction in flux. I don't have the 1 year data. We've done the sampling, but don't have the analytical back yet. So to summarize then, so this colloidal carbon technology can be used in a couple of different ways. It's commercially available. It can be done now. It can be used as a cutoff barrier, and I think that's probably going to be a good use for this. I mean, you could probably create a ring around a public supply well if you wanted to. Normally we don't do that in this field, but it could be a protective approach to buy time until maybe new technologies are developed, or maybe you have to do it periodically to protect groundwater sources. So it's enhanced sorption, or to reduce source area mass flux down gradient. So to try and kind of cut the head off these plumes, basically. Decent distribution, at least at this site. Good effectiveness after a year. You do see rapid breakthrough of some of the carboxylic acids, and we'll look after 2 years whether we're starting to see breakthrough of any of the other compounds. And we haven't, again, we don't have the 1 year data, so we don't know yet about any changes in hydraulic conductivity. I'll thank you. These are a lot of people who have funded and or worked on the project, and shoot me an email if you have additional questions, but thank you for your patience.